Okay.
Okay. So now we have to to say only clever things, I guess. Okay, so welcome everyone, and it's a pleasure for me to chair this committee on the defense of the thesis by François-Xavier Fay entitled Modeling and Control for the Oscillating Water Column in Wave Energy Conversion. And the procedure is that the candidate will have up to an hour presenting his slides, and then after that the committee, the member of the panels will make some questions. Okay, and also all the doctors which are attending this session. Okay, you have the floor. You can present it now.
Oh, okay. Well, I am François-Xavier Fay, as you said. I work in Technalia Research Innovation. I am a PhD candidate at the University of the Basque Country. Should I present anyone else? I will be presenting this work on modeling and control for the oscillating water column. I begin the presentation. Okay. Hey, I didn't understand. Sorry. I thought he was starting at 2:30. So I will change the presentation mode. Okay. Well, thank you for the introduction. In fact, Eduardo. To those who are following this presentation online, I hope you will enjoy it, as I did preparing this piece of work, and maybe you will learn something today. To begin with the outline of today's presentation, well, I will introduce the work, some motivations, some concepts. So talking about the objectives of this research, I will then move on to the main contributions that are both on oscillating water model, water column modeling and its control. I will then conclude with a summary of these contributions and open for future works. To begin with, first of all, some motivation, generalities in wave energy conversion, and also the framework for this research. So this is our planet in the solar system. It has the perfect condition for life to arise, but it has not always been this climate here. In fact, there's a natural cycle between warm periods and icing periods. In fact, at 20,000 years ago, south of Europe had the climate of northern Norway today, and our ancestors were basically hunting reindeers. So you know that this is this natural cycle between these change of temperature. And today, or nowadays, we are facing a warming period, and the global scientific community is witnessing there's a fast rise in the Earth's temperature. And this is still the industrial revolutions. So there is a link between our activities, mainly use of fossil fuels, and our emissions in the planet. But if we are imagining Earth as a system, well, it can its temperature, and it has the ability to auto-regulate itself, like a negative feedback will do it. But only when there are minor disturbances. And in the climate change and global warming, well, in fact, at some point, the disturbances begin to be so high that the system is unstable, and they can have catastrophic impacts like pack ice melting, rise of ocean temperature, ocean acidification, the loss of regulation of CO2, also the icing of permafrost. So there is a need here to act, and in fact, first of all, you have to build awareness in the global community. The government has to take and apply measures. In fact, I like to cite the megawatt scenario, which states 3 basic principles to reduce our use of fossil fuel. It is represented by the red arrow on this picture. So the first one is sufficiency. don't use the energy you don't need. The other one is efficiency. You have to think of more efficient systems. And the other one is use renewable energies. And so with that three principles, you can engage an energy transition. If you look at the past 10 years, we've seen a rapid decrease of the cost of energy production for major technologies like solar and wind technologies. And in fact, the costs were divided by 10 for photovoltaic energy and by 2 for onshore wind. And if you can see on this graph, there are this gray rectangle that represents the cost of fossil fuels. So it is not necessarily too expensive to install renewable energy capacity. In the past 20 years, here's the global trend for renewable energy capacity installation. In fact, 20 years ago, almost the majority of the installed capacity was hydropower. If you look at today, there is a huge increase and an important share of wind and solar energy. So here, I think that there is innovation is still on, but it's more incremental innovations. And I think that there is space for research and development in marine energies. So there is motivation to work on that field. In these marine energy technologies, well, we can think of tidal energy, wave energy, osmosis, ocean thermal energy. And the one I wanted to focus my work on is wave energy, because in fact, it represents a huge amount of power. And globally, well, not globally, but the resource that is accessible in Europe can in fact represent 3 times the European power consumption. Here we know that there's a huge amount of energy, and people or mankind always try to protect itself from these ocean waves, and building harbors or making more robust ships. So in fact, there are a lot of challenges here. First, we want to produce power, but it is usually associated to costly operation and maintenance. The devices to capture power have to survive winter storms. And in fact, it is also subjective to corrosion and biofouling. Now moving on to some generalities. What are ocean waves? Well, in fact, wave energy is a sort of solar energy, because the sun creates wind and the wind creates the wave. So here you see a picture of a swell wave. It is basically created by wind blowing over a large surface area far away from the coast. And you see these waves, long crested waves, coming to the shore quite regularly. And on the opposite, we can see wind waves here, and it has a much more chaotic aspect. In this picture, you see, in fact, an ocean wave is a superposition of several waves, which all one has their own amplitude and phases. And on the left side of the picture, you can see what we call a wave spectrum. And a spectrum is a representation of a sea state. The sea state is characterized by wave height and a period of wave. This shows that a wave is like a sound and vibrations. There is no transport of matter. In fact, you see here, it's the motion of the water particle due to this wave. And it is this motion we are trying to capture with wave energy conversion. There are several concepts that have been developed to capture this energy. You see first one, the attenuator, a flap type, a point absorber, one which relies on pressure differentials, pitching devices, overtopping devices, other more innovative relying on a rubber material, deformable. And the one I wanted to focus my work on, due to its simplicity and its robustness, is the oscillating water column. In this picture, you can see how it behaves. And in fact, what I wanted to state with these different concepts is that wave energy is not converging into a winning technology, like it's been the case in wind energy, where we now have the three blade horizontal axis turbine, which allows cost effectiveness and reliability. So there is still room for innovation here. Now, moving on to the scope of that research, I wanted to introduce some concepts here. So in wave energy conversion modeling, so how the devices are moving due to ocean waves. Well, we are relying on concepts of hydrodynamics, which express the motion of the device and the several forces that are in presence, like the excitation forces, which is the one that is felt by the body due to an ocean wave, also radiation forces, hydrostatic forces, power takeoff force, which is the one that we want actually to capture and to convert into useful power, and other forces which can be related to mooring forces, drag forces. And in fact, in this second equation, it's the differential equation of motion related to which relies all that forces. What's important to notice here is a device has its own hydrodynamic coefficients. Here you can see its response in the excitation components, both amplitude and phase, and also added mass at infinity and radiation damping. These coefficients can be obtained by using hydrodynamic solvers like WAMIT, NEMO, or Aqua. When you solve that differential equation with 1 meter wave for the several frequencies, you see you can extract what is called a response amplitude operator, which in fact describes the motion of a device. Here there is an example of the Mutriku frequency domain waved wire. And moving on to control for wave energy converters. Why do we want to control them? Well, of course, we want to extract power. We want to optimize the energy output. But we want to do that by assuring there is a safe and reliable operation. And also, you can apply control to assure there is a good grid connection or integration of power into the power network. Earlier, you saw the force we are trying to optimize, which is the power takeoff force. And in fact, it can be simplified as a damping coefficient, CPTO, proportional to the velocity, and a stiffness coefficient, proportional to the speed. In the literature, well, you can see that in a frequency domain, there are theoretical boundaries that are represented by the solid lines, and this type of control is called amplitude and phase matching, impedance matching, reactive control. It has several names for the same approach. And in fact, it's not very recommended in practice. It needs to have a force in the power takeoff. The power takeoff is able to give back the energy to the system, and so that it can change its motion and be closer to resonance condition. So there is another control strategy that is called latching. In fact, it's phase control, and it also tries to change the motion so we can recreate resonance. And also a passive one, which is not very efficient. What happens if we are changing the damping coefficient of that force? Well, you see, you remember the area of Mutriku, which was the blue line. And as soon as you increase the damping coefficient, you are decreasing the motion and extracting power, which you see at the lower the graphics. And globally, if you integrate, there is an optimal damping coefficient. If you integrate the power of all the frequencies, you can extract, or you can summarize as an energy production. And if we change the stiffness coefficient, well, you change the motion. There is a higher increase in the power production. The energy is in fact 3 times more important in that case. So what happens if you are optimizing both of these parameters? Well, the motion is way higher. You see, for 1 meter wave, it can, for a specific frequency, the resonant frequency, it can go up to 50 meters. Well, it's not very feasible in practice. and the total energy is like 7 times more. So you can see with this graph that you can make a parallel with the theoretical curves of maximum power extraction. Then control for oscillating water column. Here you can see the several steps of energy conversion from the wave to the wire, the electrical wire. This is why we are calling wave-to-wire models. And in fact, where can we apply control here? Well, we can apply the control at the interaction between the wave and the device, and we want here to maximize the absorbed power. This can be done by latching control for the RWC. By actuating on the latching valve, we can induce or introduce a perturbation in the pressure and change the motion of the device. Also, we can control when there is an absorbed power, we can control or optimize the energy production. And this can be done in the power takeoff. So here you have several elements of the power takeoff, turbine and generator, by using rotational speed control. And also, which is not explored in that thesis, sadly, grid interaction control. So here you want to increase the quality of power you want to inject into the grid. Some hypotheses. Well, I've seen in this research several or many references for control theory applied to wave energy conversion, most of the time in frequency domain, and several approaches for applying this control in time domain models. This is also the case for predictive algorithms, which rely, in fact, on the knowledge of the future incident wave, optimizes control parameters, so it can have a better effect in the power extraction. But these algorithms, when entering into control for oscillating systems, well, there are not that many. And in fact, real C trials for that type of algorithm in real devices in oscillating water column, I only know one of it. So there is room here for innovation, and this is one of the motivation of that work. In fact, it lacks something in the literature. Experimental results for advanced controllers, and especially for the predictive ones. And for this to reach that, we need to develop these algorithms, test them, and assess them. And to do that, we need accurate numerical models. At the same time, if you want to reach experimental and C trials, we need also to solve implementation issues. The global objective of the wave energy sector is to lower what we call the LCOE, the cost of energy production. This is in fact the ratio between the costs and the revenues. The revenues are associated with the quantity of energy you are producing. So the objective, the general goal of this thesis is to, of course, optimize this energy production by the use of advanced control strategies. And we want also to reach C trials to prove that these algorithms are actually viable. In fact, we have some opportunities here in the Basque Country. We know that there is this device which is called the Mutriku Oscillating Water Column plant. It was grid connected since 2011, has produced more than 2 gigawatt-hour of wave power and injected to the grid. And also a company named Ocean Tech, which was now acquired by Eider, developed its Marmok buoy, and it was installed in the test site close to Aminsa during two years and survived 3 winters. So here we can see that there is a room for, or there is opportunities for testing these algorithms in these 2 devices. And this was done thanks to the OPERA project. The global objective of the OPERA project is to drop down the cost of wave energy production by 2, mainly relying on 4 main innovations. One is the use of innovative power takeoff, innovative air turbine, which we will see later on, and also associated with advanced control strategies. Now we are moving to oscillating water column modeling. First of all, we'll see the model of a Mutriku plant, then of a spar type floating buoy, then the air chamber model, modeling of the power takeoff, which includes the turbine and the electrical conversion. So this assessment or this model can contribute to configure the power takeoff elements and size them. Here we see an example for Mutriku. So Mutriku, this is a side view of one chamber of the plant. This is the geometry of the plant and its surroundings, which was done to obtain the hydrodynamic coefficients. This was done by some colleagues in the OPERA project. What's important to notice here is that it is important to take into account the surroundings of the plant to capture all this changing in motion. So seabed conditions are important, neighbor chambers also, and they are all integrated into that model. What I did here is to, from these hydrodynamic coefficients, is create the time domain model. Here you can remember, or you can see the excitation force, how it is expressed, the radiation force, hydrostatic, and power takeoff. And the radiation force here, it has a term that is called the convolution integral, and we have to use some methods here to solve that, and we'll be using the Prony method in that case. Here is a graphic about the validation of the numerical model, the motion of this model, and in fact we need here to validate that the time domain has the same motion as in the frequency domain, and that proves that the approximation of the radiation force is well done. Then moving to the spar type oscillating water column, here is a side view also. What is important to see here is that it has two bodies. One is the floater and the structure, and the other one is the water column itself inside the device. And in fact, it's the relative motion between these two bodies. Each one has its own response, which creates, which absorbs the power. This model was done by a group in the University of Lisbon, IST, and I did here is the change from this frequency domain to time domain model. Here you see there's these two differential equations because we have these two bodies, and also there is an interaction between in the radiation terms from one body to another. Here is the validation also of time domain versus frequency domain. Here we are on track. So we solved the motion of the device, and now we are moving to the modeling of the air chamber. And in fact, the force of the power takeoff for an OWC is the force of the pressure inside the chamber. The pressure variations multiplied by the area of the internal water surface, the oscillating water column. But this pressure is a gas, and you can assume that it is either incompressible or compressible. We wanted to model these three. Isentropic process is kind of state of the art, and the polytropic is another contribution of that thesis. So when you think of the air as incompressible, well, here you see in this graph, it's a bit little, I'm sorry, but incompressible, it's the blue line. And in comparison with the two other processes, there is a phase shift. So there is kind of a buffer, a spring-like effect of the compressibility of air, and also a reduction of the amplitude. Basically, the difference between the isentropic and polytropic, it is that the polytropic is in fact a generalization of the isentropic, and it takes into account the efficiency of the turbine in the computation. So here we can see the difference of the power, the pressure variation for these two models. So you see that the polytropic has also lower magnitudes of power. And what is the effect of that change in the pressure variations? We see some simulation results, time series of the three powers in presence: pneumatic, absorb power, mechanical power of the turbine, and generator power, electricity. And for all of that, there is a decrease of power when assuming there is a polytropic process. Globally, when we do the simulations with several C-states, irregular C-states, we see that there is a reduction of the generator average power of between 20 and 15%. So it is important here to take into account air compressibility first, and to be sure that you are using the right model. Because we had access to the Mutriku plant, we wanted to know if this polytropic process was viable and was a good solution to implement. And in fact, we took inputs from the plant, measurement from the plant, and compared the pressure with the model we were developing. And in fact, in this specific C-state, you see that there is a quite good agreement in the pressure variation, and globally is an error of about 4%. This has to be extrapolated to also several C-states. Okay, so we solved the motion of the device. We saw that the pressure and the compressibility is important here. And now we are moving on to the power takeoff part, which is composed by air turbines. Here we are naming them self-rectifying turbines, because independently of the direction of the airflow, it is always rotating in the same direction. The turbines on the left side, they are called Wells turbines. They have symmetrical blades. There's another version with guide vanes, which tends to increase the efficiency. On the right side, it is an impulse turbine with guide vanes also, and more. There are more views in the gas turbines. This is what we call the biradial turbine. This is one that has been manufactured for the Opera project and tested in Mutriku and BMEP. In fact, the air is coming by the duct, enters into the rotor, spins it, and gets out by this big stator you see. This is all state-of-the-art, but I wanted to introduce some important equations here. There are dimensionless terms of pressure, airflow, power, and efficiency. And you see for the pressure big phi coefficient, there is an additional term, UV, which represents a safety valve, a valve set in series with the turbine. And we actually close this valve when the energy is too important in the system. So it can be used to dissipate energy. Some characteristic curves of 6 types of turbines. This is the relation between the flow rate and the pressure. An important feature of the Wells turbines is that it has a linear relation between these two quantities, and the impulse has not. You see that the yellow line is turbine number 3, is the Wells turbine of Mutriku power plant, and these characteristic curves were found in a conference paper. When moving to the efficiency curves, what characterizes the Wells turbine is a sudden drop in the efficiency. This is called aerodynamic stall. If you are flying a plane, basically this is what you want to avoid. Also the same, we have the efficiency of the turbine used in Mutriku. And what you can see also in this graph is that, well, the impulse turbines, they don't have this stall, and they can continue producing in a wider area. And the turbine number 6, the blue, light blue one, is the arc curves of the biradial turbine. So now we are moving on to the electrical conversion. So what was included in the model is a loss model of the electrical conversion at the generator. Here we are using an induction generator. So basically, loss model includes mechanical losses, or it is mainly due to bearing frictions. Also iron core losses, which is related to the magnetic field and eddy currents in the laminated plates of the generator. Sorry, yeah, iron losses. And also winding losses, which represents the heating and the loss of power by Joule effects. And it's related to the quantity of copper which is inside the generator. Also, what was introduced in these new contributions are the several operation regions of generators, like one used in the project. Basically, you have a steady region where you see here nominal torques until you can reach maximal torques. That's fine for short periods of time. And depending on the speed of the rotational speed, at some point you lose the capacity to extract power. This is called the flux weakening region. And at some point you want to stop the production when the speed is beginning to increase until a certain threshold, because at this speed there's a creation of vibrations and it can damage both the turbine and the rotor inside the generator. And this is what the use of the safety valve is for. With that numerical model, we are able to configure, to size different power takeoff systems. We see these our 6 turbines, and basically you can optimize the turbine diameter. You will be able to know what are the rotational speeds you will be working on, and some power levels also produced mechanically. So it can help also to size the generator size. Number of poles, rotational nominal speeds, nominal powers. Okay, so it's the end of the modeling part. And now we have numerical models for Mutriku, for the Sparboy, and now we want to introduce control concepts and contributions in the turbine speed control for Mutriku, using also a predictive controller for these turbine speeds. Also, predictive control for the latching control strategy in the buoy. We'll be seeing what is the approach for real-time implementation of, especially for these predictive algorithms, and results of sea trials at Mutriku and experience learned, and then results at the BMEP test site with the Marmok. So first of all, turbine speeds control for Mutriku. The first speed, which was adapted from reference state-of-the-art laws, is fixed speed turbine control. Another family is variable speed, and they rely on a torque-speed relation, like we can see in wind turbine technologies. Another one tries to improve the fixed speed and what we call the quasi-fixed speed. It relies also on a PI controller to control the speed. And the last ones, the two ones, are nonlinear model predictive control, and they can parameterize control parameters of the torque speed laws. But in fact, the first law, fixed speed, is C-state dependent, so it's not very easily implementable. And the other ones are called adaptive controllers, so they can be operated in any sea conditions. And what you see in orange are 4 new contributions of that thesis. We know we will be using the Mutriku numerical model, and the power takeoff will be the one designed for Opera. I remember we had access to the Mutriku plant, and for a period of test during the campaign, we installed what we call the pressure sensor. And this pressure sensor can give us the wave elevation, and by a process we can obtain what we call a wave climate. So wave climate is a scatter diagram, and you have a relation between sea states that are characterized by wave height and energy period here. And what I did was to extract 14 most representative C-states with a wider variety of power. And you see that this 14 C-state represents 50% of the global wave climate. And in bold here, you see the C-state number 10, which is not the most powerful, but it is the most energetic one when you take into account the frequency of occurrence. You will see in some example that this C-state will be used to show some results, because it's the most representative. Well, moving on to the first control law, the turbine fixed-speed turbine control. Well, in fact, it relies on one reference speed controlled by the PI controller. And to find that reference speed, you need this numerical model and to perform an offline optimization. So for each C-state, you find the optimal rotational speed that gives the optimal or the maximal average turbine power. And this, in fact, represents the damping coefficient in the power takeoff force we saw earlier. So there is an optimal power extraction. But remember that this control law is C-state dependent. It's not very recommended for implementation, because you have to know the C-state at each moment. Here is a time series of simulation results. You can see the torques, turbine torque and resistive torque. You see that the rotational speed is quite stable. The controller is working properly. And now we want to move on to the variable speed controls. And here the second family, the torque laws. Basically, a torque law is that depending on the speed, you apply a torque to the generator. And these curves are characterized by slope coefficients A and an exponent B. The first and the most basic speed is based on the best turbine efficiency point. So you want to set the turbine at its best efficiency, and it is associated to an optimal pressure, flow, and power. And by playing with the equations, you can extract a coefficient, KT, which multiplies the speed squared. The second law is, in fact, when we perform the optimization for the fixed speed, we saw that there was the optimal speed for the maximal, which gave the maximal average turbine power. And when you join all the dots, you saw this red line, and you can extract the A and B coefficients of that curve to characterize this law. So CL21 and 22, they are based on maximal or turbine power extraction. But what happens if we focus more on the generator operation? Here is a representation of these three laws. The first two are the blue and the red, and the black one is the one that is more optimal for the generator. And here the power takeoff that we'll be using has a nominal speed of 150, and we want the curve to go until its nominal torque, which is around 200. Basically, here are some time series of how these algorithms or these different torque laws are behaving. And we can see quite clearly that the law relying on the generator concerns apply torque levels that are much more important. And this is done, in fact, because the other control laws are applying generator torque lower at certain values, and the speed is getting higher until reaching the maximum. And there is, in fact, an actuation of the safety valve, so it has to dissipate energy. Okay, now we are moving to what we call the quasi-fixed speed law. It is similar to CL1, but we want to solve the issue of the dependency of the C-states. So we have to find a way to change the reference speed, but with process variables or with operating variables. And here we are using pressure. When we compute that pressure and we include it into a sliding standard deviation, it's a moving window of about 3 minutes here. We can obtain the standard deviation. We multiply that by a certain gain, and we obtain a reference speed. This is what is shown in this equation. And in fact, this gain is obtained by the optimal parameters that were extracted earlier for the offline with the offline optimization. And we make the average of this gain for all the C states, and you're done. Here are some simulation results. You see that in comparison with the fixed speed law, there is a change of the speed, both the reference and the feedback speed, and you see that it has a more stable shape than with the torque laws. And what we can see here also is that this change of speed reference quite follows the energy of the set of waves coming. Okay. Now we are moving to a nonlinear model predictive control that has been developed in that work. So you see that, or you know that it can adapt and process optimization using future wave excitation, and the numerical model that has been developed with all these nonlinearities, with the air chamber, the turbine efficiency, generator loss model. This graphic here shows the process and the approach for the optimization. And in fact, at a certain point, we trigger the optimization over what we call a prediction horizon. This is around a two-wave period. And during that time, we optimize the control parameters, A and B, slope and exponent, so they will characterize the torque speed curves. And we do that at each replanning period. And the replanning period can be basically half of the prediction horizon. So there is, to perform this optimization, what's important to have is the objective function. But here we want to maximize average powers, not only for the turbine or for the generator, but both of them. And you see here there are coefficients, weighting coefficients, alpha and beta, so we can set more importance to the turbine or the generator conversion. And we wanted to include additional constraints in another version of that law, because we witnessed that these controllers were always tending to maximize the power extraction, and we wanted to include additional concerns of reliabilities for the components in the power takeoff. So here the same, we see a time series of simulation results for these two versions of the model predictive control. And the generator torque the simulation results are the same for a certain period of time. And what you see on this orange box are the different approach, and the fact that at some point the second version tries to lower the power extraction and dissipates energy by the use of the valve to have a better reliability score. And here you see that the A and B coefficients, the evolution, at the beginning they are the same, at the final the same, and there is a change of approach between these two controllers. You see that basically the first version always wants to maximize the power extraction, and the second one has additional concerns on the component's reliability. In this picture here, you can see the four torque speed approach. The three are the torque variable speed families based on offline or generator consideration. And the blue dots are in fact several shapes or several torques of the predictive controller. So you see that it can populate a wider area while the other controllers are quite static. So it can in fact adapt to the both external conditions with the waves coming and internal conditions, because all the components and the motion are taken into account. Now we are moving to the results, the simulation result part. In this graphic is kind of a summary, so we can compare all the control algorithms. This is done with the annual energy production. So we take basically for all the C states the generator average power, and we multiply it by the number of hours of operation. Obviously, CL1 is the one that produces more energy, but we'll take the most simple torque law as a reference to compare the power production. And in fact, the other state-of-the-art variable speed increases 20% close in reference with that reference. The other torque law based on the generator consideration increase 40% the annual energy production. The quasi-fixed speed 50%, the same as the first version of the predictive algorithm. And the second version, well, dissipates a bit more energy, but still there is an increase of 40%. With this simulation results, I wanted to divide and to show the average generator power. So you can see that at the in some of the C states, the lowest energetic, it is almost the same power extraction. But then from C state 10 to 14, it starts to have a significant difference. So this is, we are able to compare this algorithm with performance results. But also I wanted to include here some score or reliability score. Because when we compute standard deviation of the generator power, this means that we are taking into account power peaks in the C state, and we see globally that some controllers are more concerned about have additional concerns of power takeoff components, and you see that the second version of the predictive algorithms at the end divides by 2 the standard deviation in comparison with the first version. So it is effective, and it is well working as we expected. And now closing the chapter of speed controllers, we are moving on to the implementation in simulation of predictive latching control, which is based on pressure thresholds. In fact, we are using the same algorithm as previously, but in fact, instead of optimizing the slope and exponent, we want to optimize pressure thresholds. When there is the pressure variation, when the pressure is going over these thresholds, it will order the valve, the shut-off valve in front of the turbine to close and open. And by this opening and closing, we were able to change the motion of the device, and this is what we want to prove with that algorithm. So first, pressure variations with using regular waves. You see that with the blue line, there is these regular changes in pressure, and when we trigger the predictive latching algorithm, you see a different evolution of the pressure. And also the green line are the changes of valve actuation, or 0 off, closed, and 1 open. Okay, so we saw that there is an effect on the pressure here, and we want to see if also it has an effect on the motion. So we take here in this graphic the excitation force and the relative velocity between the two bodies. And if you remember, if you want to create resonance condition, we want the phase of the excitation force and of the velocity to match. And in fact, this is what is shown on this graphic. The red curve is when the latching strategy is on, and there is a change of phase. It's becoming to be closer to the excitation force, and also we see an increase in the amplitudes. So in theory, or with these regular waves simulations, we see that there is a huge increase in power production. But when we go to irregular waves, well, there is still an increase, but not as important as we expected. And in fact, globally, with taking several systems, we see an increase in the generator average power of around 6 to 25%. So still there is an increase, but you have to balance between the complexity of the algorithm and the results here. So this algorithm was not selected to test then in real sea conditions. So now moving on to the real-time implementation. So to make sure that we can bring the model predictive control into Mutriku and BMAP, we want to make sure that they will work properly. So for that, we are using a test rig, a test bench to perform the validation. And basically, the test bench used is composed of two electrical machines, a motor and the generator. And from one side, there is what we call the emulation of the device. So the motor will provide the torque similar to the turbine. And on the right side, you have all the real components in the power extraction that are the generator, the power converter, and the control unit. For this was based on XPC target configuration, so we could easily play with our numerical models and well, make some tests in this infrastructure. And the implementation, in fact, of the predictive algorithm was done in an external PC that had some connections with the test bench to avoid overloading the control unit. But this is a picture of the real setup in Technalia that was used. Okay, so we need to adapt the numerical models because the real components we will be using have some capacity, nominal speeds or nominal powers that are different of the ones in the test bench. So we need to apply a scaling approach. We are using float scaling because it is the scaling methodology which relies on gravitational forces and one presence in wave energy conversion. So we need to compute that scaling coefficient and adapt it for the quantities like speed, torque, and inertia. To perform the validation, well, basically we have the same numerical models running in parallel. One will be strictly simulated, and the other one has input and output to the test bench. So we are able to compare the results, both experimental and numerical. So here are some results of two C-states. You have the quantities of rotational speed, torque of the turbine, the generator torque applied, and also included the evolution of the control parameters A and B. And you see with the changes of these AB parameter that there is also a sudden change in the generator torque, both up and down. And we wanted to make sure that these changes were viable, and so we make plenty of tests, and we saw that this working operation did not affect the generator. So now we have the controller validated. We know that it works in a control unit. We know that it will not be harmful for the system. So we are now moving. We have another thing to solve, is the excitation force estimation or computation, because we need this excitation force, so the model is then able to apply its optimization process. So we need to compute that excitation force. And in Mutriku, you remember we had this pressure sensor installed in front of the plant. So we know that we can have the value of the wave elevation, and we connected this value and integrate it into the control unit, where we can compute the excitation force. And in the literature, we see that there is this computation time domain of the excitation force is a convolution between Kx, which is an impulse response function for the excitation, and the wave elevation. we see there's the same as for the radiation. There is an convolution integral to solve, and we are using the same method as explained earlier. Here is a graph about what to validate if this approach is correct, and in fact it is. You see that there is error between the modeled excitation force and the computed one, which is around 10 or minus 10%. So it actually works. Now we solve all that issue of implementation, so we can move on to the Mutriku power plant, implement all these algorithms, and in fact we were able to test for 2 weeks in June 2018. This was the sea states that were in presence during that testing campaign. Well, June is not known for its highest energetic sea states, so we were witnessing waves of between half a meter and 1 meter, but still we had the chance to test over 325 half an hour tests, and we wanted to compare the torque speed, simple torque speed law, using this maximum power law you saw, and the predictive controller. So the procedure was to run one algorithm for half an hour and to change from the other one for another half an hour, and so on. So we were capable of having the same sea states in 1 hour, basically. So we were able to compare them. Well, talking about the predictive algorithm, we need to initialize the prediction horizon time and the replanning period. In fact, well, we know that the pressure sensor is static. We know the distance between the two, but we need to compute the maximal predictive horizon, so the maximum time we have for the process. And in fact, when there is a change of tide level, because we are quite close to the coast, the travel time of wave can change. And here is a way to compute the time delay in function of the water depth. Okay, so we wanted in the first test to validate the implementation of the predictive controller, and one way to do that is to set the control coefficients far away from their optimal and to run the algorithm for several hours. Here is a test of 20 hours, and we see that there is an evolution of the control coefficient until reaching convergence. We didn't witness any cut or any problem with this implementation, so we know that it can converge to a solution and there is no interruption. We were also able to compare and validate the numerical model with the process variables because we had values of the numerical model with the implementation process, and we had measurements from the sensors. And here there are three variables of importance: the velocity, the position for the motion, and the relative pressure. And you see that in fact the model underestimates some of the values. So there is still room for improvement. If we want to compare the power production results, so first of all there is these results of electrical power on average for all the sea states and with the simple torque law. You see the results are printed with the box plots, so we can see the minimum values, maximum values. The blue rectangle represents 50% of the test, and the star, the average of the average electrical powers. So now, with the test of the model predictive control, the results are shown in fact as a comparison with the other controller. So we see that it's always increasing, and the average of average are about 13% to 65%. So there is a good increase in power here. And in fact, when we take into account the frequency of occurrence of the all sea states, we can have a weighted average, and the improvement in power extraction for the model predictive controller is higher than 30%. So it is quite encouraging. If we are focusing not only on the power extraction, but on the efficiency of the power takeoff components, well, we can see that the simple torque law tries to optimize the turbine efficiency. Here you see the several dots are each half an hour test, while the predictive, the NPC, tries to focus on the global power takeoff efficiency. And this is why the production is higher, because it takes into account not only the turbine or mechanical energy, but both, well, all the components of the power takeoff. And this is a major improvement. Okay, so we know that results were encouraging in Mutriku. So we had the opportunity to test at the BMAP site with the Marmok buoy. And here is a bit the framework of the test. So we have a wave buoy that is situated in front of the Marmok buoy, and it can send wave elevation to an onshore computer. This onshore computer performs the optimization process and can send to the PLC the A and B coefficients. And there is another version of the MPC, which was developed in collaboration with the partners from the University of Sevilla, which tend to put this optimization algorithm directly inside the PLC. And we actually managed to do it. Same as before for Mutriku, we need to know what is the distance between the wave buoy and the Marmok. This is done by computing with GPS position the distance between them two. But also we know that the velocity of waves, phase velocity, can depend on the water depth and on the wave period. At each beginning of test, we computed the phase velocity to obtain and initialize the prediction horizon and the replanning period. Same as for Mutriku, we wanted to make a conversion test. So here you see the evolution of the control parameters for a 3-hour test, another one for a 5-hour test. And what I forgot to mention also is that these tests were run during June, but 1 year later, 2019. So we were not lucky to have a wide variety of sea states, and the majority of sea states were around 1 meter. The same as before, we wanted to highlight the fact that the MPC can cover, can populate the scatter diagram of the generator torque in function of the rotational speed. So it proves that it's the same, it's not static, it can adapt to the conditions. So that's a good improvement. When we are focusing on performance results, well, in fact, when doing the test in the Marmok, when Marmok is developed by a company, and we had some confidentiality issues or concerns, and we could not show the results in function of the sea states and show the same comparison. But what we did have as a result is average efficiencies in function of Hermes values of the pressure. So here you see that in average the efficiency is quite high. We were not able in that test to compare with the simple torque law. So we have only the two predictive controller. The basic difference is in the implementation of these controllers. And also we can see results for the average generator power. And here we see that in function of the generator load, which is the ratio between average generator power for this test over the nominal power of the generator. And you see that there are two different areas, or one is strictly close to a line which is close to global generator efficiency curves. And there is another cluster here. So it proves that depending on the predictive algorithm, it can adapt and have several shapes and show different results. Okay, so as a summary of the contributions, I would say that we managed to have or to develop what is today the most accurate numerical wire-to-wire model today, because this is what is in the literature. We were able to develop 5 advanced control strategies. Some of them are based on MPC algorithms, and also one with latching control. We were also able to provide the critical assessments, both taking into account performance and reliability. And also we've seen first real-time implementation and show C-trial results for predictive control algorithm in turbine speed control. And to conclude, we note and we saw that there was a clear need for accuracy in the numerical models, and especially for the predictive controller. We need to have best accuracy with the nonlinear terms or nonlinear concepts like compressibility, power takeoff. And also we saw that the MPC algorithms have the potential to greatly improve the power production. And in fact, it has a negligible capex. So we can prove that there is a decrease of the LCOE while using predictive controllers. And additionally, we saw that there is a higher complexity when we are doing real-time implementation of predictive controllers. So moving on to future works, well, in fact, we know that there is still room for improvement in the wave-to-wire model in the Mutriku plant when we compared the numerical and the measurements. We need also to test the predictive algorithms in a wider variety of sea states. And because the tests were done only in summertime, so we are not able to see the clear improvements in reliability of the constrained predictive controller. Also, what could be interesting is to implement in the optimization process not only an optimization and maximization of powers, but of a global LCOE optimization, taking into account reliability scores, for example. Also, what could be interesting also is to focus on grid integration issues, because we know that wave energy production will create peaks of power, and that can generate some issues with the grid. And why not thinking of energy storage system to try and smooth this power output? And finally, we had access to a huge quantity of results during those sea trials, and we can think of a way to use these results and use artificial intelligence algorithm to try and find some patterns and select control algorithms and get rid of the MPC implementation, the estimation of forces, or the complexity in the implementation. One final word, if I may. When I asked someone to explain me what is a PhD thesis, well, he did draw a circle representing the human knowledge. At the beginning, you go to school and you have global knowledge increasing in all directions. When you enter into university, you do your bachelor and you start to specialize in one direction. In the master, you go deeper and farther when you're starting your PhD and you read papers. So finally, a thesis is this little bubble in the human knowledge, and I hope that this work I presented today can help and can inspire other academics or people in the field to continue developing this wave energy conversion, so we can have a higher increase of marine energies in the global mix. So this is it for my side. Thank you very much for your attention, and then I will be happy to hear your questions if you have some.
Okay,